To conclude the section 2.4 notes, we'll now look at example 5, looking at some graphical examples of determining domain and range. Example 5 says, assume that for the graphs of the functions shown, the axes are marked in 1 unit intervals. State the domain and range of each function. The questions we want to answer here are, for the domain, what is the smallest possible x-coordinate for points on the graph? What is the largest possible one, if there is one? And are there any gaps in between? So for domain, we want to focus on the projection of the graph along the x-axis. And note that the graph here extends, this would be -4 here. Each of these marks is 1 unit on both the x and the y-axis. That's what's understood here. So this extends from -4, and then you can see that as far as the x's are concerned, there's no gaps as we move from -4 to the right, and the x's just get larger and larger, apparently going to the right forever to positive infinity. So with this in mind, we would say that the domain D would be bracket -4 comma infinity. So all x's greater than or equal to -4. For the range, we'd focus on the projection of the graph along the y-axis. And again, here the question might be, what's the smallest possible y? What's the largest possible y? In terms of the smallest possible y, that would appear to occur at y equals -2 at this point. The biggest one would appear to occur up here at y equals 3. And it would appear that we would get every y value in between. There are no gaps in the y values. There are many y values that get repeated. For example, y equals 1 gets repeated all along this part of the graph. But in any event, the smallest y value would appear to be -2, the largest 3, and we get everything in between. So the range could be expressed as -2 to 3 with brackets, meaning we are including -2 and 3, the endpoints, in the interval. So that's imagine just pushing the graph against the y-axis and determining what part of the y-axis gets covered, and you would see it's this part right here. Okay, so that's our first example. Next one, part B. You can see there's clearly a gap in the graph. For the domain, it would appear that the x values will extend to the left forever and to the right forever. So the domain will extend to -infinity and to positive infinity. There is a gap, however, in the x's that starts at -2 and then begins again at -1. Now there's an open point here. This means that this particular point is not included on the graph. So that means x equals -2 itself is not included in the domain. But the solid point at -1 indicates that that point is included on the graph. So -1, x equals -1 is included in the domain. Putting all of this together, we would express the domain as follows. From -infinity to -2, but not including -2 because of the open point. Then we pick it up again. There's a gap between -2 and -1 where there are no x values. We pick it up again at -1. -1 is included because of the solid point. And then the graph continues to the right indefinitely. So we would go out to positive infinity. We connect these two individual pieces to write it as a single set by putting a union symbol in between. So it's the union of these two intervals. What about the range? You may be surprised and think that the range should have two separate intervals as well, but actually it's not necessary. If you project the graph along the y-axis, there is actually no gap in the y values. Now you might think, well, what about right there? Isn't there going to be a gap in the y's? Well, actually not, because all of the y's that are missing in that gap are filled in right through here on the other part of the graph. So if you project the graph against the y-axis, the whole y-axis is going to get covered. In other words, there are going to be points corresponding to every possible y-coordinate. So the range is simply the set of all real numbers, minus infinity to infinity. There are no gaps in the y-coordinates, even though there is indeed a gap in the graph itself. Now finally, for part C, domain and range. Okay, again, we want to think in terms of what's the minimum value, what's the maximum value for x coordinates. This point out here, again, each of these is one unit. This is 1, this is 1. This actually would be -9 out here. You can see there's obviously a gap here at 1, 2, 3, 4. This is -5. Then there's a gap here at 2. I'm just going to indicate these. You can see that there's an endpoint of the graph here at -9, so that's the smallest x coordinate you can get. The graph does appear to go to the right indefinitely, so it would go to positive infinity. Are there any gaps in x values? There are certainly two gaps in the graph, but if you look at each gap, there is a point associated with the x coordinate at which the gap occurs. At -5, there is a point that has an x coordinate of -5, and at 2, there is a point, a solid point that has an x coordinate of +2. So there actually are no gaps in the x coordinates, even though there are two gaps in the graph. Therefore, the domain can be simply stated as the set of all real numbers, the set of all real numbers greater than or equal to -9. That is, -9 to positive infinity. The smallest x value is -9, so we do have to stop the set there, but it does extend to positive infinity without any additional gaps. Okay, what about the range? If we project the graph against the y-axis, are there any gaps in the y's? Well, there's certainly a gap here, and there might be a gap here. Now, right here, this is y equals -4. And you do see there is a gap in the y-coordinates. There are no points with y-coordinates between -4 and -2. Now at -2 there is a y-coordinate because there's a solid point there. At -4 there's a number of points right along here where you have y-coordinates of -4 as well. So the way we would state the range, for the horizontal line we would just say you just repeatedly get -4. So I'm just going to write that as a set unto itself. So you have all the points on the horizontal part that have the same y-coordinate of -4. We use just the curly braces to indicate that, since it's just a single number. And then we want to connect that with a union to the set of y-coordinates between -2, and it would appear that the largest y value we can get would be up here at positive 6. And then the graph levels off and doesn't rise any further. So it would appear that we get all of the y values between and including -2 and 6. And that would include everything right here, because you can see there are y coordinates that are going to fill in that gap, even at this open point here, which occurs at y equals 2. There's a point on the graph that has y equals 2 as a y coordinate. So y equals 2 is included in the domain, in the range as well. So the range here is a little bit tricky. Hopefully you can see what I'm referring to, although it's a little bit messy, I will admit. If we look at example 6, which is a continuation of an analysis of this graph. By the way, notice how the graph passes the vertical line test. That's just something I want to point out. All of these graphs in examples 5 and 6 pass the vertical line test. They are functions. That is something to pay attention to. Notice even the points where you have an open point and a closed point. There's a closed point and there's an open point. There's not two closed points. So if you draw a vertical line through those points, it will only intersect the graph at one point. Okay, now I have to move kind of quickly so I can finish this video within the 15-minute time limit I have. For the graph of function g of example 5c, find g of -3, g of 2, and all values of x such that g of x equals 4. G of -3, what are we looking for? We're looking for the y-coordinate corresponding to x equals -3. Okay, well, where is -3? X equals -3 is right here. So it's the y-coordinate at this point right here. And that y-coordinate appears to be 0 because you're right on the x-axis. So it would tell us g of -3 equals 0. G of -3 is the y-coordinate corresponding to x equals -3. What is g of 2? Okay, here we're looking at x equal to 2. Well, that would correspond to the y-coordinate at the solid point, not the open point, but the solid point above x equals 2. Notice that has a y-coordinate of 3. So it must be the case that g of 2 equals 3. And all values of x such that g of x equals 4. Okay, well, where is g of x equal to 4? It would be right there. G of x is equal to 4 means y is equal to 4. Okay, now there are actually a couple of x values. There's an x value corresponding to this point and to this point. There are two different points where the y coordinates are 4. One of those occurs at -1. The other one occurs at +3. So if g of x is equal to 4, it follows that x could either equal -1 or 3. Both g of -1 and g of 3 are equal to 4. So you can have more than one x associated with a given y, but you cannot have more than one y corresponding to a given x. So that concludes the notes for section 2.4.